This is the second section on the chapter on resolving forces, and it's going to be the first time that we look at inclined planes. In other words, things on a slope. Everything we've done so far has been on a flat area. So we've had basically questions pretty much like this, where something is flat like this. Even things with pulleys, they've been on a flat area. Maybe we've got friction going this way. We've got like a normal reaction. We have the mass going down. We have some sort of pulling force that we'll call F there. Maybe it's moving in that direction. Everything's been like that. But what if we have something like this? So something is on a slope. What do we do now? Well, there's a few things that we need to do. We want to make the working as easy as possible. The first thing is whenever we looked at forces before, we looked at forces going up or down or left and right, and we decided whether they were balanced or unbalanced depending on whether it was accelerating or in equilibrium or moving at constant speed. When something is on a slope, it is easier to look at forces which are parallel to the plane. In other words, forces which are going either this way or this way, and forces which are perpendicular to the plane. In other words, forces which are going like that. It's much easier than trying to do forces going in those directions. Yeah, trying to do it like that is too hard. Yeah, and we want to make things as easy as possible. So I'm going to draw a diagram out here like this and label most of the things, the types of things that we could have. So I've got some sort of mass here on a plane. Let's give it a mass m. There's still going to be a normal reaction, but remember the normal reaction is perpendicular to the plane. So look at the direction it's pointing in. It's at a right angle to the plane, and the plane is now at an angle. What's that angle? Well, it will depend on the question. So let's call this angle theta. Now, how about the weight of that mass? Well, the weight will still point down. It's still going to be pointing this way, always. And let's say that we've got some sort of force pulling it up. So let's say we've got a force that's pulling up like that. And maybe there's some sort of resistance here. Okay. Now, I always want to look at the forces parallel to the plane, so forces which are going that way, or perpendicular to the plane. Now there's one force that's not going in either one of those directions. That's this one here. So what do? I split it up into its horizontal and vertical components. Now watch carefully. When I draw that force, it's going to look like this. One part going opposite to the normal reaction, perpendicular to the plane, and one part going parallel to the plane. Now that's really important because so often I've seen students draw that incorrectly. So it's really important that when you draw those forces on, that this one here, okay, this one must be perpendicular to the plane. So it's going in the opposite direction to the normal reaction, and this one must be parallel to the plane. If you draw your diagram and it's not parallel or perpendicular, you've done it wrong. So I often see things like this. So let's do something that's wrong. Where a student got this mass on here, they draw down mg like this, and then they go on and they maybe do something like this with some sort of right angle here. Now neither one of those arrows is parallel or perpendicular to the plane, so you know that that's wrong. It must be like this. Watch out for that. And on these questions, you're given plenty of space in the paper. Draw your diagram nice and big so you can get all those forces on there. And then everything is the same as before. We look at the forces going this way, so in parallel to the plane, so that'd be FR, F, and this bit here. And let's put those on. So oh yes, let's add this on as well. This angle here is always the same as this. You can use simple rules to prove that that angle is the same, which means that this side is always going to be mg cos theta, and this side down here, which is parallel to the plane, is always going to be mg sine theta. Yeah, you'll see that when we do some examples. Okay, often a diagram isn't drawn, so let's draw one here. Right, so we've got a block of mass 10 kg. So let's put 10 kg there. Okay, it's sliding down a smooth slope, so there's no resistance, and it's asking us to draw all the forces on there. So it says that it's angled at 15 degrees to the horizontal. So there we go. Draw all the forces. Right, what do we have? Well, we have a normal reaction here. We have going straight down 10g. We need to split that force up into its two components, one parallel to the plane, one perpendicular to the plane. This angle up here is also 15. It'll always be the same as the incline to the plane. And the force opposite the normal reaction, that is going to be 10g cos 15, and this one down here is going to be 10g sine 15. There we go. We put all the forces on the diagram. We've actually put the size of some of them as well. Calculate the size of the normal reaction. So this is part A. Now, this thing isn't moving in that direction. It's moving in this direction. Now, if it's not moving in that direction, it means the forces going that way are balanced. And what are the forces going that way? R going up and 10g cos theta going down. So it means that R equals 10g cos 15. I think I said cos theta, cos 15. Okay, that's it. There are no other forces. The one going up equals the one going down. So 10 times 9.8 times cos 15, 94.66. So 94.66 newtons is the normal reaction. Part C, the acceleration, right. It says it's sliding down the slope, which means that the force going down the slope is bigger than any going up the slope. There are no forces going up the slope because there's no resistance, there's no force trying to stop it from sliding down. So the only force causing it to slide down is this. Now this is different to things which are on flat surfaces. Things that are on slopes will start to slide down and accelerate on their own without any other force. Gravity, its own weight, is causing it to slide down. That makes sense. So we now have, using F equals ma, the resultant force, or the only force, is 10g sine 15 equals ma. Now the mass is 10, so 10a, so that means that a equals 10g sine 15 over 10. Well, let's cancel out the 10 straight away. There's no point multiplying by 10 and dividing by 10. And just do 9.8 times sine 15. And I get 2.54 if I round. So A equals 2.54 meters per second squared. So there's my answer for the acceleration. And again, look at the size of the acceleration. Is it a sensible value? It shouldn't be really bigger than 10 if something's just sloping down. Probably less than 5 is a sensible answer for things just sliding on their own or moving from rest, unless, as I said before, it's something like a bullet or a rocket or something like that. SpaceX. Right. Here we go. A particle is being of mass m, is pushed up a slope by a force which is acting at an angle, and it's causing to accelerate. Show that the mass of the particle is that. First thing, put all your forces on the diagram. Right, so the mass is m, so we have, going straight down, mg. What else do we have? Well, we have the normal reaction up here, which we may or may not need. Is a smooth slope, so there is no resistance, but we do have forces that need splitting up, so that the forces either point perpendicular to the plane or parallel to the plane. So the ones I draw in green are going to be the ones that I want. So we want that and that. We know that this angle here is 30 degrees, always the same as the incline of the slope. And we want this force needs splitting up, so it goes like that and that. Okay. Right, so let's work out the size of those forces. I'm going to try and draw them in a diagram. There's not a lot of space. So force over here is mg cos 30. This one down here, mg sine 30. Moving up to the top, this is 60 degrees here. I know, like, there's 60 degrees below it, but that's basically 60 degrees. So that means that, actually, let me just draw it a bit bigger so it's nice and clear. So something like that. I don't know if that helps. Right, so that means that the force over here, which is perpendicular to the plane, is going to be 5g sine 60, and this one down here is going to be 5g cos 60. Okay, right. So we want to show, and we know the acceleration, let's put that on as well. So it's going to be accelerating this way, and that's 0.5 meters per second squared. Right, so let's start with the forces which are parallel to the plane. That means the forces which are going in that direction or even that way. So the ones which are parallel to the plane. Because it's accelerating in that direction, it means that the force pushing up is bigger than the force going down. So the resultant force is going to be, well, what's pushing it up? 5g cos 60. Anything else going up that way? No. What's going down? Or mg sine 30. And that will equal ma. So mass times acceleration. Like that. Can we simplify that? Are there things that can cancel down? Let's have a look. Let's work some of these things out. So 5g cos 60. Is that a nice number? Yes, 24.5. So let's change that to 24.5. Minus mg cos 30. So that's half mg equals 0.5 m. Okay, we'll leave that like that for the moment because we may not need to work out m, but we've got that. Oh yes, we do need to work out m. What am I talking about? Let's get rid of that then. So that means that if we move both the m's across, so we'll have 24.5 equals 0.5 m plus half mg. Let's factorize it. 24.5 equals m 0.5 plus half g. Okay, so m equals 24.5 divided by 0.5 plus half g. 24.5 divided by 0.5 plus 0.5 times 9.8, and I get 10. So the mass of this thing is 10. Now, I didn't even need to look at the forces in this direction. I didn't even need to use that. It was there if I needed it, but in that direction there's only one unknown, and that unknown is m. We know everything else, so that did the job. That's nice. Okay, so let's put on the forces onto this diagram. Actually, let's draw a bigger one down here, bigger version of it. So you've got this angle here, angle of alpha. We're told that the mass of this thing is 2 kilograms, so 2g is the weight. We have a force of 4 newtons pushing up, which is parallel to the slope. This force will need splitting up into its components. This angle here is alpha, the same as it's always the same as the incline to the slope, which means that this part is 2g cos alpha, and this bit is 2g sine alpha, and there's also a normal reaction here. We may or may not need that, but I just want to draw your attention to the angle, the way that the angle is given. Notice that we're not told what the angle is. We're told that the tan of the angle is 3/4. So we could do the tan inverse of 3/4 to find theta. not theta, to find alpha. We could do that, but there's a more accurate way. Let me show you how to do it. So tan we can refer to a right angled triangle, and let's call the angle alpha that one. So if the tan of that angle is 3/4, that means that this side is 3 and that side is 4. I recognize that triangle. That must mean that this side is 5. Now, could I actually now work out what cos of the angle is and sine of the angle? Yes, I can. Cos alpha adjacent over hypotenuse, not tan alpha, we've just done tan, sine alpha opposite over hypotenuse, and looky over here, cos alpha, sine alpha. So why not replace those with exactly what we know they are? So instead of 2g cos alpha, we could write 2g times 4/5, because that's cos alpha, or even 8/5 g. And instead of 2g sine alpha, why not 2g times 3/5, because that's what sine alpha is, or 6/5 g. Now, doing it that way, you don't need to deal with any sort of tan inverse and then do the sine of that and the cos of that, because quite often those angles are going to be long decimals. So if I did the tan inverse of 3/4, I get 36.869897 and so on. And if I round that number and just round it to 37 degrees and then do the cos of 37 degrees and sine of 37 degrees, I've missed a trick. I'm going to end up with actual inaccurate answers. We should never round until you get to your answer. So always try and use the exact values where you can and only round at the very end. Right, so we are trying to work out the acceleration. So the acceleration is going to be in this direction. So we're going to do resultant force equals ma. The resultant force is going to be the 4 that's going up minus the 6/5 g that's going down, the 2g sine alpha. That equals ma. And that's pretty much it. A equals 4 minus 6/5 g over 2. Let's work that out and see what we get. 4 minus 6/5 times 9.8. Divide that by 2. Minus 97 over 5, or 25, which is negative 3.88 meters per second. So all that means is it's slowing down. Yeah, that's all it means. It's still going up the slope. You can have a negative acceleration. That doesn't change the direction. It just means that it's slowing down as it goes up the slope. It's decelerating. Okay, now I should be able to do exercise 5b on pages 98 to 99 of the textbook.